Most of us remember the 1940s as an era of heavy steel, of Sherman tanks and massive battleships. But the secret that actually saved the Allied cause wasn't made of armor plate. It was made of thin, fragile glass. While Hitler's V-1 buzz bombs were raining down terror on London with a sound that still haunts the memories of a generation, a group of American tinkerers in a converted Chevy garage were betting the war on a literal light bulb. They were told it was impossible to put a radio inside a cannon shell, that the physics of the blast would turn it to dust. Today, we're looking at the invisible Sentinel, the 15-cent miracle that turned the deadliest robot bombs in history into mere target practice.
Many of us look back at the 1940s as a time of industrial muscle, of steel, smoke, and massive gears grinding out the machinery of liberation. But if you were standing on a London street corner in the summer of 1944, the threat you faced wasn't coming from a gear, it was coming from a sound. It was a guttural, terrifying rattle that sounded like a motorcycle engine failing in the sky. It was the V-1 flying bomb, the buzz bomb, and for a long time we were essentially defenseless against it. You see, the problem with the V-1 wasn't just its speed, it was the math of interception. At the time, anti-aircraft gunners were using technology that hadn't fundamentally changed since the Great War. You fired a shell into the sky and hoped for a direct hit, or you set a mechanical timer and prayed it exploded near the target. Imagine trying to hit a speeding bird with a pebble while you're standing on a moving train. That was the reality. Our best gunners were firing thousands of rounds just to bring down a single pilotless drone. The V-1 was a robot, it didn't feel fear, and it was winning the war of attrition. But while the steel was failing, a group of scientists were betting the future on something far more fragile, a tiny glass vacuum tube. To a casual observer in 1943, the idea of putting a delicate glass radio tube inside a high-velocity artillery shell was worse than a joke. It was a scientific impossibility. If you've ever dropped a light bulb on a hardwood floor, you know exactly why the military skeptics laughed. A standard artillery shell, when fired, experiences a centrifugal force of nearly 20,000 Gs. It's not just an explosion, it's a violent tearing of reality. The consensus was clear. You cannot put a brain in a bullet. The tube would shatter before it even cleared the barrel. The miracle of the glass bulb wasn't just about radio waves, it was about the sheer, stubborn American refusal to accept that glass was weak. The reality of the situation was a breakthrough in ruggedization that sounds like science fiction even today. Scientists at the Applied Physics Laboratory didn't just build a radio, they built a radio that could be dropped from a skyscraper and still work. They took these tiny vacuum tubes and potted them in specialized resins and waxes, essentially creating a solid-state block that defied the laws of physics. This was the Proximity Fuze. Unlike a timed fuse, which relied on a guess, this glass bulb acted like a primitive bat. It emitted a continuous radio signal. When those waves bounced off the metal skin of a V-1 and returned to the shell, the frequency shifted, the Doppler effect in action. When that shift reached a specific threshold, the shell didn't wait to hit the rocket. It didn't wait for a timer to tick down. It simply knew it was close enough to kill. It transformed the sky from a place of misses into a web of invisible tripwires. But having the technology was only half the battle. We had the brain, but we were still losing the war on the ground. The British were skeptical, the Americans were secretive, and meanwhile, the V-1s were raining down on London at a rate of 100 a day. The stakes weren't just about a new gadget, they were about whether the capital of the free world would be burned to the ground by a machine before the glass bulb could ever be tested in the field. We often find our greatest strengths in our most fragile innovations. As we look deeper into the development of Section 52, we see that the laughter of the skeptics was about to be silenced by the sound of 82% accuracy, a number that in the world of 1944 was nothing short of a divine intervention. To understand the sheer magnitude of the breakthrough we're discussing, we have to first look at the grim reality of the math that preceded it. For those of us who grew up in an era where technology is expected to be precise, it's almost impossible to imagine just how blind our defenses were in the early 1940s. We weren't just fighting an enemy, we were fighting the laws of probability. Think back to the last time you saw a professional baseball player try to hit a 90-mile-per-hour fastball. Now imagine that ball is actually a 2,000-pound explosive moving at 400 miles per hour. Then imagine the batter is 2 miles away and he's trying to hit that ball with another smaller ball. That was the deadly arithmetic facing the Allied gunners. In 1944, a standard 90mm anti-aircraft gun was a marvel of mechanical engineering, but it was being asked to perform a miracle. To bring down a V-1 buzz bomb, a gunner had to account for the speed of the target, the wind at various altitudes, the humidity, and the time of flight, the seconds it took the shell to actually reach the target's altitude. The math was heartbreaking. Statistically, it took an average of 2,500 shells to bring down a single German aircraft. If you can picture a pile of 2,500 brass casings, each weighing about 20 pounds, you start to see the industrial burden of failure. We were literally filling the sky with lead and hoping a piece of it would accidentally intersect with a piece of the enemy. Why was the accuracy so abysmal? It came down to the fusing. At the start of the V-1 campaign, we had 2 ways to make a shell explode.
First, there was the contact fuse. This required a direct hit, steel on steel. But at the speeds these machines were traveling, the target wasn't just small, it was practically a ghost. A shell could miss a V-1 by 6 inches, the distance between your thumb and pinky, and it might as well have missed by a mile. The shell would simply continue upward until it reached its peak and fell back to Earth, often causing friendly casualties on the ground. The military relied on the second method, the mechanical time fuse. This was essentially a high-grade pocket watch built into the nose of the shell. A gunner would use a rangefinder to estimate the altitude, dial a time, say 15.2 seconds, and fire. But here is where the arithmetic turned deadly. If the timer was off by even 1/10 of a second, the shell would explode 50 or 60 yards away from the target. In the world of high explosives, 60 yards is a miss. You weren't just fighting the Luftwaffe, you were fighting the tolerances of a clock spring. When the V-1s started falling on London, the failure of this math became a national crisis. The V-1 wasn't like a piloted Heinkel bomber. A pilot might flinch or dive or turn. The V-1 was a straight-line robot. It was predictable, yet we still couldn't hit it. The British called it the doodlebug because of its erratic engine sound, but there was nothing cute about the result. Because our anti-aircraft shells were so inefficient, the only way to stop a V-1 was to hope an RAF fighter pilot was brave enough and fast enough to fly alongside it and tip it over with his wingtip. It was a desperate, suicidal tactic born from the fact that our guns were failing. Many of us remember the stories of the Blitz, but we often forget that the second Blitz by the V-1 was in many ways more psychologically damaging. You could hear the engine. You knew that as long as it was making noise, you were safe. But the moment the engine cut out, the moment the math of its fuel ran out, it was coming down, and our defenders were standing there with 2,500 shells for every 1 kill. By July of 1944, the arithmetic suggested that London could not survive. The cost of the shells we were firing was nearly as high as the damage the V-1s were causing. We were throwing a fortune into the clouds and getting almost nothing in return. The brass in Washington and London were staring at the charts with a sense of impending doom. They knew about the secret projects in the States, but they didn't believe they would work. They had been told for years that close only counts in horseshoes and grenades. But they were wrong. They were about to learn that if you could change the deadly arithmetic so that close actually counted in the air, you wouldn't just save a city, you would change the nature of warfare forever. The failure of the mechanical fuse wasn't just a technical hurdle, it was the catalyst for the most secret project of the war, one that would move from the drawing board to the coastal batteries of England in a race against time that felt like a heartbeat. In the annals of the Great Crusade, we often think of the massive Oak Ridge facilities or the sprawling hangars of Boeing, but some of the most pivotal victories of the 20th century didn't begin in a cathedral of industry. They began in a place many of us would recognize from our own youth, a nondescript, slightly grease-stained used car garage. By 1940, the National Defense Research Committee realized that if they were going to solve the deadly arithmetic we just discussed, they couldn't do it through the slow, bureaucratic channels of the traditional military-industrial complex. They needed a group of disruptors before that word was even a marketing term. They recruited Merle Tuve, a physicist with a jaw made of granite and a mind that didn't recognize the word impossible. Tuve didn't want a shiny new office in D.C. He knew that secrecy was his greatest weapon, and nothing is more invisible than the ordinary. Therefore, he set up shop in a converted Chevrolet dealership and garage in Silver Spring, Maryland. Imagine it. While the world's most dangerous robot bombs were being drafted in high-tech German wind tunnels, the Allied countermove was being plotted on workbenches that still smelled of motor oil and exhaust. To the neighbors, it was just a bunch of engineers working late on radio parts. But inside, Section 52 was engaging in a scientific street fight. The facts of Section 52's operation are a testament to the grit of that generation. They weren't just thinking, they were breaking things. Tuve's philosophy was simple. If a component can't survive being shot out of a cannon, it doesn't belong in his garage. To test their designs, they didn't use sophisticated simulators. They bought a 57mm anti-tank gun, hauled it out to a farm in Virginia, and fired their prototypes directly into a haystack. They would then spend hours digging through the hay to see which tiny glass tubes had survived and which had turned into dust.
Many of us remember the old tinkerers of the mid-century, men who could fix a tractor with a coat hanger and a bit of prayer. That was the spirit of Section 52. They weren't looking for the elegant solution, they were looking for the tough one. They realized that the primary enemy wasn't the Luftwaffe, it was centrifugal force. History suggests that the biggest hurdles are often solved by the smallest details. The problem they faced in that garage was that even if the vacuum tube survived the explosion of the gun, the internal filaments, those tiny wires inside the glass, would vibrate and snap like a guitar string in a hurricane. But then, the team at Section 52 had a garage logic epiphany. If you can't make the wire stronger, you have to make the environment more rigid. They began experimenting with potting the electronics, filling the entire shell head with a specialized hard-setting wax and resin. This was revolutionary. By encasing the delicate radio components in a solid block of plastic-like resin, they essentially turned a collection of fragile parts into a single, indestructible brick. It was the birth of ruggedized electronics. Every time you drop your modern cell phone and the screen stays on, you owe a debt of gratitude to the men in that Silver Spring garage who decided to pour hot wax over a radio. But as the success grew, so did the paranoia. The miracle of the glass bulb was so potent that the Joint Chiefs of Staff were terrified it would fall into enemy hands. If a single unexploded shell landed in German-occupied territory, the Nazis could reverse engineer it in months. For the first few years of the project, Section 52 lived under a water-only rule. The Proximity Fuze was strictly forbidden from being used over land. It could only be fired over the ocean, where a dud would sink into the Atlantic mud, safe from German eyes. This created a massive tension. The engineers in the garage knew they had the cure, but they had to watch from the sidelines as the V-1 started hitting London. They were sitting on 10,000 words of data and a mountain of working fuses, while the British public was being told to simply duck and cover. The garage was no longer big enough. By 1942, Section 52 had outgrown the Chevy dealership and moved to a larger facility that would eventually become the Johns Hopkins Applied Physics Laboratory. But the garage spirit remained. They had proven that a radio could survive a cannon blast. But now they faced a new conflict. Survival was one thing, intelligence was another. Could this miniature radio actually talk to a V-1 in the split second it took to pass it at 400 miles per hour? The skeptics weren't finished yet. They argued that even if the radio survived, the signal would be noisy, or it would trigger prematurely because of the clouds, or it would simply fail to see the target in the dark. Therefore, the story moves from the grease and oil of Silver Spring to the saltwater spray of the testing grounds, where the impossible engineering of Section 52 would finally meet the reality of the firing line.
To truly appreciate the genius of Section 52, we have to look past the what and focus on the how. For many of us who have spent time under the hood of a car or tinkering with a home radio, we know that electronics are, by nature, fussy things. They like to be kept cool, dry, and stationary. But the engineers in that Maryland garage were asking a radio to do the exact opposite. They were asking it to become a weapon. In the 1940s, the idea of a miniature radio was an oxymoron. A standard living room set was the size of a microwave and filled with glowing, hot, fragile glass tubes. To the military brass of the era, the suggestion that you could shrink that technology down to the size of a pint of cream and then shoot it out of a gun wasn't just impossible, it was seen as a waste of taxpayer money. The first impossible hurdle was the vacuum tube itself. At the time, tubes were made for radios that sat on mahogany tables. They had long, delicate filaments that provided the electron flow. If you tapped one with your fingernail, you could hear the ping of the vibration. The engineers at Section 52, working with companies like Raytheon and Sylvania, had to reinvent the manufacturing process from the ground up. They developed sub-miniature tubes, tiny thumb-sized components, where the internal structures were reinforced with extra mica spacers and shorter, thicker filaments. But even a tough tube is still a glass bottle. History suggests that the breakthrough didn't come from making the glass stronger, but from changing how the glass sat in the shell. Many of us remember the old trick of putting an egg in a jar of water to keep it from breaking when dropped. The engineers did something similar. They used that potting compound, a mix of Ceres wax and later a plastic resin, to ensure that under the 20,000 Gs of a cannon blast, the internal components didn't move a fraction of a millimeter. If it couldn't move, it couldn't break. What's truly remarkable, and this is a fact that often gets lost in the history books, is that this wasn't just a simple trigger, it was a complete 5-tube radio transceiver. The nose of the shell acted as the antenna. Inside, one tube acted as an oscillator, generating a continuous radio frequency. When the shell flew through the air, it was essentially screaming a silent radio tone into the sky. The second impossible hurdle was the Doppler effect. As the shell approached a metal object, like the wing of a V-1, the radio waves would bounce off the enemy and return to the shell. Because the shell was moving so fast, the returning waves were squashed, changing their frequency. The tiny brain inside the shell had to detect that specific frequency shift, filter out the noise of the ground or the clouds, and decide in a millisecond, I am close enough. If you've ever left a flashlight in a drawer for a year, you know that batteries are the weak link in any device.
For an artillery shell that might sit in a damp warehouse for 2 years before being used, a standard dry cell battery was useless. It would leak, corrode, or simply go dead. The engineer's solution was a stroke of garage logic genius, the reserve battery. Inside the fuse, they placed a small glass ampule filled with a highly corrosive electrolyte, sulfuric acid. In storage, the battery was dead because the acid was contained, but when the gun was fired, the massive shock of the explosion shattered the glass ampule. The spinning of the shell, centrifugal force, flung the acid outward into a series of plates. In the time it took for the shell to travel from the breech to the muzzle, the battery woke up. It provided full power for exactly 2 minutes, just long enough for the flight, and then it died forever. It was a battery with a shelf life of a decade and an operational life of a heartbeat. But here arose a terrifying conflict. If you have a shell that explodes whenever it gets near something, what happens when it's still near the gunners? The Navy was terrified that the fuses would detect the barrel of the gun or the ship's own superstructure and explode instantly, killing the crew. Therefore, the impossible engineering had to include a series of fail-safes. They designed a mercury switch clock that used the spin of the shell to slowly move a physical barrier. The shell had to spin several thousand times, meaning it had to be hundreds of yards away from the ship before the firing circuit was even connected. It was a mechanical arm's length that ensured the miracle weapon didn't become a suicide pact. By the time the design was finalized, the VT Fuse was the second highest priority project in the United States, surpassed only by the Manhattan Project. But while the atomic bomb was about one massive explosion, the VT Fuse was about millions of tiny ones. At the height of production, the U.S. was churning out 70,000 fuses every day. Think about that. Every day, 70,000 impossible radios were being hand-assembled, potted in wax, and shipped across the Atlantic. The skeptics had stopped laughing. They were now looking at the data from the testing grounds at Dahlgren and Indian Head. The shells weren't just working, they were performing with a consistency that defied everything the old guard knew about ballistics. But the final test wasn't in Maryland. It was in the cold, salt-sprayed batteries of the English coast. The glass brains were about to meet the robot bombs in a fight for the survival of London. Therefore, the stage was set for Operation Diver, a high-stakes gamble where the Americans would hand over their most guarded secret to the British, hoping that a 15-cent radio tube could stop a 10,000-pound vengeance weapon. In the summer of 1944, the streets of London were under a siege unlike any in history. For those who lived through it, the V-1 buzz bomb wasn't just a weapon, it was a psychological terror. You'd hear that stuttering pulse jet engine, a sound like a giant angry lawnmower in the sky. As long as it was making noise, you were safe. But the moment the engine cut out, a heavy, suffocating silence fell over the city. You had about 12 seconds to find cover before the ton of high explosives hit the ground.
By July, over 100 of these doodlebugs were being launched every single day. The British defenses were reaching a breaking point. They had tried everything: barrage balloons, fighter interceptions, and massive anti-aircraft batteries. But as we discussed, the deadly arithmetic was failing them. For every V-1 destroyed, hundreds of thousands of pounds of lead were being fired into the air to no avail. This was the moment of the great gamble. It was called Operation Diver. The United States had been sitting on the Proximity Fuze, the glass bulb miracle, with a grip of iron. General Eisenhower and the Joint Chiefs were terrified. They knew that if the Germans got their hands on a single dud and reverse-engineered the radio technology, our bomber fleets over Europe would be wiped out in a matter of weeks. The water-only rule was still in effect. The fuses were for the Navy, to be used over the open ocean, where failure meant a watery grave. But the situation in London was dire. Therefore, Churchill made a personal plea to Roosevelt. The gamble was this: bring the most secret electronic technology of the war to the very edge of the English Channel.
If the guns were positioned on the coast, any shells that failed to explode would fall into the sea, keeping the secret safe. In a massive logistical feat, the Americans shipped over 1 million VT fuses to the UK. But they didn't just send the hardware, they sent the men who knew how to use them. Many of us remember the stories of the Red Ball Express, but there was a similar, quieter rush of scientists and technicians from Section 52 flying across the Atlantic to train British gunners on how to handle these delicate, wax-potted miracles. General Frederick Pyle, the head of Britain's anti-aircraft command, made a radical decision. He realized that the existing defensive layout was wrong. The guns were scattered across the countryside, where they had to worry about falling shrapnel hitting civilians. Under Operation Diver, he ordered every single heavy anti-aircraft gun in England, over 800 of them, to be uprooted and moved to the coast of Kent and Sussex. In less than 4 days, thousands of tons of equipment and tens of thousands of personnel were shifted to the shoreline. This created a wall of lead right at the water's edge. But it wasn't just lead anymore. For the first time, these guns were equipped with the SCR-584 radar and the Bell Labs M9 predictor, coupled with the VT Proximity Fuze. This was the first time in history that an integrated, fully automated sensor-to-shooter system was used in combat. The radar found the V-1, the computer calculated the lead, and the proximity fuse ensured that the shell didn't need to hit the target, it only needed to get close. The results of this gamble were nothing short of a statistical impossibility. Before the VT fuses arrived, it took an average of 2,500 rounds to down one V-1. On the first day of the coastal deployment, that number dropped significantly. By the second week, it was down to hundreds. But then the gun crews began to understand the glass bulb. They realized they didn't have to wait for the perfect shot. They could saturate the path of the V-1, and the shells would do the rest. The turning point was August 28, 1944. On that single day, 94 V-1 rockets crossed the English Channel, headed for London. In the past, maybe 10 or 15 would have been intercepted, but with Operation Diver in full swing, the coastal batteries, using the impossible engineering from a Maryland garage, destroyed 82 out of 94 targets. Think about that, an 87% kill rate against a target that just months prior was considered nearly untouchable. However, this success created a new, unexpected conflict. The RAF fighter pilots, the few who had saved Britain in 1940, were used to being the primary defense. They would chase the V-1s over the channel, often flying through their own anti-aircraft fire. But the VT fuses didn't care if a plane was a doodlebug or a Spitfire. If a British pilot got too close to a V-1 while the coastal guns were firing, the proximity sensors would trigger on the Spitfire just as easily. A strict no-fly zone had to be established over the coastal gun belt. It was a blow to the ego of the RAF, but the math was undeniable. The machine was better at killing the machine.
We often talk about the miracle, but for the men and women on those coastal batteries, many of whom were members of the ATS, the Auxiliary Territorial Service, it was a grueling, deafening existence. They lived in tents on the wind-swept cliffs, surrounded by the constant thunder of 90mm guns firing around the clock. They saw the V-1s coming in low over the water, trailing fire and smoke. They knew that if they missed, that doodlebug would be over a London suburb in less than 10 minutes. The pressure was immense. But as the 82% accuracy reports started coming back, the atmosphere changed. There was a sense of awe. They were watching shells explode in midair, seemingly by magic, shredding the pulse jets before they even reached the white cliffs. The gamble of Operation Diver had paid off. The most secret weapon of the United States had been revealed to the world, not through a spy or a leak, but through the thunderous success of the coastal batteries. But the V-1 was only the beginning.
As the war moved deeper into Europe and the Pacific, the Proximity Fuze would be called upon to do something even more dangerous, move from the safety of the coast to the chaos of the front lines. The water-only rule was about to be broken, and the consequences would change the face of land warfare forever. The number 82% might sound like a dry statistic from a boardroom report, but in the late summer of 1944, that number was the pulse of a nation. To the people of London, it was the difference between a peaceful night's sleep and a neighborhood leveled by a ton of Amatol explosive. For the men of Section 52 back in America, it was the final validation of a 4-year-long impossible dream. But how did we get from 2,500 shells per kill to an 82% success rate? It wasn't just the technology, it was the marriage of the machines. By late 1944, the British coast wasn't just a line of defense, it was the world's first fully automated kill zone. Many of us remember the transition from manual labor to automation in the American factories of the 50s and 60s, but that transition actually happened on the cliffs of Dover in a matter of weeks. The breakthrough came when the VT fuse was combined with the SCR-584 radar. Before this, a human being had to squint through an optical rangefinder and manually shout coordinates to a gun crew. Humans are slow, and humans get tired. The SCR-584, however, was a radar system that could lock on to a target and automatically steer the guns to follow it. The human element, the greatest source of error, was removed from the equation. The radar found the target, the M9 computer calculated the lead, and the gun fired. But the final, most crucial piece of the puzzle was the glass bulb. Even with the best computer, a direct hit was still a gamble. The VT fuse turned that gamble into a sphere of influence. The facts of the 82% breakthrough are staggering when you look at the raw data. In the first few weeks of the V-1 campaign, anti-aircraft guns were only bringing down about 17% of the bombs launched. It was an embarrassment. But as the VT fuses reached the front lines in massive quantities, the curve didn't just rise, it spiked. By the final week of August 1944, the efficiency climbed so high that on one particular day, the batteries destroyed almost every single V-1 that entered their sector. The purple secret was the burst pattern. When a standard timed fuse shell exploded, it created a small, localized puff of shrapnel. If the V-1 wasn't exactly at that spot at that microsecond, it flew through unharmed. But the VT fuse was designed to explode at the optimal distance, about 70 feet from the target. At that distance, the shell didn't just hit the V-1, it shredded it. The 82% accuracy wasn't about hitting the bullseye, it was about making the bullseye 100 times larger. The sky over the English Channel became a cloud of steel. The V-1s, with their thin sheet metal skins and delicate pulse jet engines, simply couldn't survive a proximity blast. They were being swatted out of the air like flies. For those of us who appreciate the weight of history, we know that weapons change more than just the battlefield, they change the spirit of the people. Before the 82% breakthrough, the V-1 was seen as an invincible weapon of the future. The Germans called it the Vergeltungswaffe, the vengeance weapon. It was designed to make the Allies feel that their technology was obsolete, but the glass bulb flipped the script. The V-1, for all its terrifying sound and fury, was a dumb weapon. It flew in a straight line at a constant speed. Therefore, the smart technology of the proximity fuse turned the German miracle into an expensive flying target practice. The predator had become the prey. The pulse jet engine, once a harringer of doom, became a dinner bell for the coastal batteries. But here is where the story takes a dark and necessary turn. As the V-1 threat was neutralized, a new conflict arose. The war in Europe was stalling, the Battle of the Bulge was looming on the horizon, and the Allies were facing a massive shortage of manpower. The success on the coast had proven that the VT fuse was the most lethal anti-personnel weapon ever devised. If it could shred a metal V-1 in the sky, what could it do to an infantry division in the woods? The water-only rule, the ban on using the fuse over land to keep it from the Germans, was the only thing standing between the glass bulb and the German army. General George C. Patton, a man who had no patience for scientific secrets if they didn't kill the enemy, began screaming for the fuses. He saw the 82% accuracy reports from the coast and realized that if he could use those shells in his howitzers, he wouldn't need to hit a foxhole. He could just explode the shell above the foxhole. The silencing of the pulse jet was the final nail in the coffin for German long-range terror. By September 1944, the V-1 launch sites in France were being overrun by Allied ground troops. The Germans tried to move the launches further back, even trying to launch them from Heinkel bombers over the North Sea. But it didn't matter. The wall of lead on the coast, powered by the 82% efficiency of the VT fuse, was impenetrable. The V-1 campaign, which Hitler had hoped would force Britain out of the war, had failed completely. Not because of a lack of German ambition, but because of a tiny wax-filled radio tube, a tiny miracle of engineering.
We often talk about the atomic age, but the electronic age of warfare was born right here. The 82% breakthrough proved that information, the ability of a shell to see its target, was more important than the size of the explosion. Therefore, as the last of the V-1s were falling into the channel, the men of Section 52 weren't celebrating. They were already packing their bags. They were headed to the Ardennes forest. The glass bulb was about to go to its first land war, and the deadly arithmetic was about to be applied to the German Wehrmacht in a way that would haunt the survivors for the rest of their lives. As we look back through the fog of the 20th century, we tend to remember the giants, the B-29 superfortress, the Sherman tank, and the mushroom cloud over the Pacific. But history suggests that the most profound shifts in human conflict often happen on a scale that is nearly invisible to the naked eye. The invisible Sentinel, that tiny wax-potted glass tube, didn't just win a battle on the coast of England, it fundamentally rewrote the rules of the world we live in today. For years, as we've discussed, the VT fuse was kept under lock and key, restricted to the waves of the ocean to protect its technical secrets. But in December 1944, during the bitter, frozen chaos of the Battle of the Bulge, the water-only rule was finally discarded. General Patton, facing a desperate German counteroffensive, was given permission to use the proximity fuse on land. The effect was devastating. In the dense woods of the Ardennes, German soldiers were accustomed to taking cover in foxholes or behind trees to shield themselves from artillery. But the invisible Sentinel changed the geometry of death. The shells didn't burrow into the soft mud or shatter against tree trunks. They detected the ground from 30 feet up and exploded in midair. The foxholes became graves. The shrapnel rained down vertically, bypassing every earthly defense the Wehrmacht had. Patton later wrote to the War Department, stating that the funny fuse had won the battle for him. He called it the most important contribution to the war effort, next to the men who fought it. It was the first time in history that air-burst artillery became a reliable, push-button reality. Beyond the battlefield, the facts of the VT fuse's legacy are even startling. Many of us who spent our careers in industry or engineering recognize that the path to the modern computer didn't start with a clean slate. It started with the ruggedization pioneered by Section 52. Before the proximity fuse, electronics were furniture, delicate, stationary, and prone to failure. The man in that Maryland garage proved that you could make a circuit survive 20,000 Gs. This was the direct ancestor of the black box flight recorder, the solid-state electronics in our cars, and even the guidance systems that took us to the moon. The truth is that the mass production of the VT fuse, 70,000 units a day, taught American industry how to manufacture high-precision electronics at scale. We didn't just learn how to build a better shell, we learned how to build a world where technology is everywhere.
When you look at the smartphone in your pocket, you aren't just looking at a phone, you are looking at the distant, sophisticated grandson of a 1944 anti-aircraft shell. There is a certain nostalgia in the silence that followed the V-1 campaign. By the time the war ended, the doodlebug was rendered obsolete. The 82% accuracy rate we've discussed didn't just stop a weapon, it killed a concept. The era of the slow, predictable flying bomb was over before it had even truly begun. But the conflict didn't vanish, it evolved. The success of the Proximity Fuze forced the development of faster-than-sound jets and ballistic missiles. The invisible Sentinel had raised the bar so high that the only way to beat it was to move faster than the speed of a radio wave. As we sit here today, reflecting on those years of sacrifice and ingenuity, it's worth noting that the names of the men in Section 52 aren't as famous as Oppenheimer or Patton. They were the quiet professionals, the tinkerers, the physicists, and the garage mechanics who saw a problem and refused to believe it was impossible. They represent a specific kind of American spirit that many of us remember fondly, a time when we solved problems with our hands and our heads without needing a trillion-dollar cloud network to tell us what to do. They took a glass bulb, some hot wax, and a radio signal, and they built a shield that saved London and shortened the war by months. Therefore, the legacy of the Proximity Fuze isn't just found in a museum or a history book. It's found in the safety of our skies, the precision of our technology, and the freedom of a continent that was once shadowed by the wings of robot bombs. It was a miracle of the mundane, a testament to what happens when we stop laughing at a crazy idea and start digging through the haystack to see what survived the blast. The 82% accuracy was the statistic, but the invisible Sentinel was the soul of the machine. And as the last of that generation passes the torch to us, we would do well to remember the glass bulb. It reminds us that even in our most fragile moments, with the right engineering and a bit of grit, we can stand against the most terrifying storms and come out on the other side.
The story of the Proximity Fuze reminds us that the greatest victories often come from the smallest, most overlooked details. But history is rarely a closed book. Many of you watching may have your own memories of this era. Or perhaps you worked with the very ruggedized electronics that these glass bulbs inspired in the decades that followed. If you found value in this deep dive into Section 52, I'd be honored if you'd join our community by subscribing. We're dedicated to preserving these stories of ingenuity and grit that defined a generation. Before you head off, leave a comment below. Did you know how close we came to losing the deadly arithmetic of the sky? Or is there another forgotten innovation you think deserves its own documentary? I look forward to continuing the conversation with you in the comments.